Okay, friends, in this video, we are going to discuss nuclear reactions like nuclear fusion, nuclear fission, spallation reactions, and their examples also. Okay, and it is a part of nuclear chemistry. So let's start nuclear reactions, that is nuclear fission. Fusion first. So what is nuclear fusion? In nuclear fusion, you can see in this diagram that there is a nucleus, like this is the, for example, this is a nucleus where there are three neutrons, one, two, and three, and two protons. So this is a big nucleus. We will say it is a big nucleus. Okay, there are two protons and three neutrons. Now, how it is formed? Now, we have to understand how it was formed or it is formed. So initially in nuclear fusion reactions, there are two small nucleus are there. First, for example, first is deuterium and second is tritium. Tritium has two neutrons, one and two, and one proton. Likewise, deuterium has one neutron and one proton. When they are fused together, जब वो दोनों क्या होते हैं आपस में fuse होता है, तो they form a big nucleus. Like it has now three neutron and two proton. Two proton comes from deuterium from one from deuterium and one from tritium, and three neutron, two from tritium and one from deuterium. So now this is the big nucleus, formation of big nucleus. So this is the fusion reactions where two, we can say that two small nucleus combine or fused together and form a heavy nucleus. Heavy nucleus. Okay. And during this process, energy is released, high amount of energy released, and small subatomic particles like alpha particles or maybe beta, maybe gamma, or neutron can be released. Okay, so we can say that in nuclear fusion reaction, there are two small nucleus combine or fuse together and form a heavy nucleus, and during this process, a huge amount of energy is released and subatomic particles are also released, like helium means alpha particles or neutron. So this is the nuclear fusion reaction. Now we can understand, or we have to understand the nuclear fusion with the example. For example, we know that in nuclear fusion, two small nucleus are combined. For example, there are two nucleus, one H1 and one H2. These are small nucleus, they will combine and they will form 2He3 plus gamma. Gamma particles are, subatomic particles are released. Okay, mass of one H1 is 1.00785 unit. Mass of one H2, 2.01410 unit. Mass of 2H3, 3.0160929 unit. Okay, so now we have to calculate the mass defect. What is the mass defect? Mass defect is 1 point this one, mass of reactant. Okay, so mass of reactant means small nucleus. 1.00785 plus 2.0071410 minus जो product nucleus, mass of product nucleus. Okay, so minus 3.016029. Now it is 0.00589 unit, and if you want to calculate it into kg, then we have to multiply it with 1.66 into 10 to the power minus 27 kilogram. Okay, so it comes 9.791 into 10 to the power minus 30 kilogram. So this is the mass defect. Now binding energy or energy released is equal to mc square. M represents mass defect, so we have to put the value 9.799 into 10 to the power minus 3 into velocity of light 3 into 10 to the power 8. Okay, so at the end we are having, or we have, is equal to 8.81 into 10 to the power minus 13 joule. This is the binding energy. Okay. Now, second example is estimate the amount of energy released in the nuclear fusion reactions like this 1H2, 1H2, 2H3, and 0 neutron 1. So given that 1H2 mass is given, 2H3 mass is given, and Mn mass is given. Okay. So where Mn means neutron. So where 1 U is equal to 1.66 into 10 to the power minus 27 kilograms. So express your answer in unit of mega electron volts. First, we have to calculate the delta M mass defect. It is 0.0035 into 1.66 into 10 to the power minus 27 kilogram. Now, E is equal to delta MC square, and we will put the value and you will get the answer. So, initially, how do we solve this question? Solution is mass of 21H2 is 2.014 into 2. So, it is 4 to 4.02 at 2 unit. Mass of 2H is 3 plus neutron. So 3.0160 it's given. Plus neutron mass is given. So that's why it is 4.0247 U. Now we have to calculate the delta M. Delta M observed minus calculated. So 4.02 at 2 minus 4.0247. It is 0.0035 U. And delta M is this. If you want to calculate into kg, and delta MC square, so 0.00, almost 0, near about 0. So binding energy is E is equal to delta MC square. So this is the answer. So with this way, we can understand the nuclear fusion. Now, nuclear fission reaction. What is nuclear fission reactions? In nuclear fission reactions, a big nucleus is converted or splitted into small nucleus or higher, lighter element. So this is the, for example, uranium-35. It is the big nucleus, and it undergoes bombardment of neutron, and it is split into, or it is divided into two lighter element, and huge amount of energy or neutron is released. When neutron is released, these neutrons again not reuse. This neutron is utilized for the same process. Okay, so process is continuous. So this is uranium-235. It gives two lighter element. Neutron is released. This neutron again bombard on the heavy nucleus, and it again gives two lighter element, and this process is continuous. So this is the nuclear fission. So nuclear fission reactions, we can say that energetic neutrons the bombardment of energetic neutrons on the heavy nucleus gives lighter element, and huge amount of energy is released, a neutron may be released. Okay, and these neutrons again used for bombardment on the heavy nucleus, and this process is continuous. So this is nuclear fusion reaction. So basic difference nuclear fission and fusion. In fusion, there is two nucleus gives one nucleus, two lighter nucleus gives one heavy nucleus, and in nuclear fission, one heavy nucleus gives two lighter nucleus. With this example, we can also understand. For example, this is the heavy nucleus, and it is 235 uranium. It is converted, or it gives krypton and barium, those small nucleus. Okay. Now again, neutron, and in this process, neutrons are released, and these neutrons again used for bombardment on the uranium. So again, this process is continuous. Neutrons are released, and heavy element like 235 uranium gives lighter element, and this process is continuous. So this is the nuclear fission reaction in simple way. Now, energy released in nuclear fission reaction. So this is the example to understand the energy released or released energy from fission reactions. So this is suppose neutron, this is uranium, neutron is bombard on the neutron uranium. It gives 92. First, this uranium converted into 92 to 36. Then it gives two small nucleus like barium and krypton as compared to this, and three neutrons are released. So this is the simple expression of nuclear fission reactions. Now we have to find the energy release. Okay, or Q. Q is the energy release. So mass of uranium-235, that is 235.04395 unit. Barium mass this, krypton mass this, neutron mass this. Okay. Now we have to calculate the Q, and Q can be calculated like this: E initial mass minus E final mass. So what is the initial mass? It is one neutron and one uranium. So that's why this is the mass of uranium plus mass of neutron, and this is the final mass. Final mass, that is mass of barium plus mass of krypton plus mass of 3 neutron. So it comes 0.19000 unit. Now Q, if you want to calculate it into mega electron volt, so just we have to use, or we have to multiply this by 931.494 mega electron volt per unit. So it comes 176.984. So with this way, the energy released during nuclear fission. So we can calculate the nuclear fission energy released during the nuclear fission process. Now you can understand the difference between nuclear fission and nuclear fusion. Okay, so in nuclear fission, there is a bombardment of neutron on heavy nucleus, and this heavy nucleus is giving lighter elements or lighter nucleus with neutrons. In nuclear fission, two small nucleus combine and gives the heavy nucleus, and this heavy nucleus again released a huge amount of energy or subatomic particles. So this is the basic difference between nuclear fission and nuclear fusion reaction. Now, this is a very important nuclear spallation reaction. What is nuclear spallation reaction? Nuclear spallation reaction is a nuclear reaction whereby a high energy hadron strikes a nucleus and imparts energy to the nucleus, leading to the emission of a number of nucleons from it. Means in nuclear spallation reactions, what happens? High energetic hadron. What is hadron? Hadron is a class of subatomic particle to which neutron and proton belong. Means what is the hadron? Hadron contains proton or neutron, or these are subatomic particles belonging to proton and neutron. So hadron strikes on the nucleus, and it gives energy and the emission of another nucleon. This spallation process in two stages. First stage is the intranuclear cascade, and second stage is evaporation. First is internuclear cascade, where high energetic proton attacks a nucleus and subatomic particles are released. While in second stage, that is evaporation, means nucleus itself, we can say nucleus itself boils and released subatomic particles. Now we will discuss these two stages of nuclear spallation in detail one by one. So first stage is intranuclear cascade. Intranuclear means within the nucleus. Okay. So reaction probability: when passing through matter, a 200 mega electron volt hadron with two Fermi wavelength interacts only with individual nucleons within the nucleus. Means, for example, this is the nucleus, and this is the proton, and this is the neutron, and suppose this is heavy nucleus. Hadron, high energetic hadron having two Fermi wavelength and 200 mega electron volt energy. Now it attacks on not on nucleus, but it attacks on individual nucleon. Okay, and then subatomic particles are released. So this is the nuclear spallation reaction. Nuclear spallation reaction is specific where high energetic hadron attacks or interacts with the individual nucleons. Individual nucleons means whether it can attack on proton or neutron individual. Then huge amount of energy is released. The probability of spallation reactions occurring depends only on the average density of nucleus and not on nuclear properties. So this spallation reaction depends on the density of average density of nucleus, but it doesn't depend on nuclear property. Nuclear property means nuclear charge, nuclear mass, and like that. So material and nucleon density. Water, this one, aluminum, this, and this. Okay. So we can say that is nuclear spallation in nuclear spallation reaction, high energetic hadron attacks in the nucleus or attack on individual nucleon and huge amount of energy of subatomic particles are released. So the incident in hadron means which hadron is going to attack. Transfer a fraction of its kinetic energy to the stuck nucleus. This stuck nucleus it wants to attack, so it transferred its kinetic energy. Okay, the hadron nuclear interactions may transfer energy to the nucleus as whole through subsequent interaction with neighboring nucleons, leaving the nucleus in a highly excited state. So just see a high energetic proton or high energetic hadron attacks on nucleus and specific subatomic particles are released. Produce pi meson as reaction product. This is the pi meson. It is also subatomic particle. Eject the energetic and forward directed nucleons from the nucleus. It can eject the proton or neutron like nucleons from the nucleon. So this is the intranuclear cascade of nuclear spallation reaction. Now second stage is evaporation. What is evaporation? The highly excited nucleus boils. Boils means it is highly excited. Of nucleons, mostly neutrons or cluster of neutrons as nuclei in hydrogen and helium atoms. For example, this is the nucleus, and here there are proton and neutrons also. So highly excited nucleus evaporate the neutrons from itself. So that is evaporation. For each nucleon emitted, the nucleus de-excited by the binding energy of the nucleons, which is about 8 mega electron volt. When it releases neutrons from itself, then then it gets stabilized, having energy like 8 mega electron volt. Each emitted neutron has 2 or 3 mega electron volt kinetic energy. जितने neutrons निकल रहे हैं, they have 2 or 3 mega electron volt energy. These evaporation particles are emitted nearly isotropically. Isotropically, this evaporation happens. So this is the second stage of nuclear spallation. तो spallation sources और potential application कौन-कौन सी है इसकी अपन को that we have to understand. Okay, so nuclear neutron scattering research, it is applicable to nuclear scattering research, nuclear waste transmutation, energy production, isotope production, rare isotopes for nuclear physics research, medical isotopes, research isotopes, neutron source for nuclear physics research and nuclear cross-section measurement, irradiation facility for radiation damage studies. So for such kind of purposes, these nuclear spallation reactions are important or applicable. Now, nuclear cross-section. What is nuclear cross-section? So to characterize the probability that a certain nuclear reaction will take place. So probability that a certain nuclear reaction will take place, it is customary to define an effective size of nucleus for the reaction that is called as cross section. Means how much probability is there that nucleus will undergo nuclear reactions. Okay, for that purpose, the effective size of nucleus is required. So that size is cross section, and it is defined as sigma is equal to r by I, where I sigma is a cross section, I is number of incident particles per unit time per unit area, r is number of reactions per unit time per second, and it is generally expressed in the term of barn, where one barn is 10 raised to the power minus 28 meter square. So this is the nuclear cross section. So what is nuclear cross section? Nuclear cross section in simple word, nuclear cross section is the probability of a nuclear reaction in a nucleus or for a nucleus, the effective size of nucleus is known as cross section. Now, radioactive isotopes. Radioactive isotopes. What are radioactive isotopes and their application that we will discuss. So radioactive isotopes is also known as radioisotopes. Radioactive, why do we call them radioactive isotopes? It means radioactive, whenever we use the radioactive word, it means then we are talking about unstable nucleus. Okay, unstable nucleus. So radioactive term represents unstable or denotes for unstable nucleus. These are also known as radioisotopes. Isotopes which are unstable and continuously emitting the radiation, those are known as radioactive isotopes. Any of several species of same chemical element with different mass whose nuclei are unstable. So what are radioactive isotopes? In simple word, radioactive isotopes means isotopes with unstable nucleus. So this is radioactive isotope. Uh, dissipate express energy by spontaneous emitting radiation in form of alpha, beta, and gamma. So it has an unstable nucleus. That's why it will release alpha, beta, or gamma radiation. Radioactive isotopes have many useful applications in medicine. For example, cobalt-60 is extremely or extensively employed as radiation source to arrest the development of cancer. So radioactive isotopes have a huge application for especially in medicine. For example, cobalt-60, which is used for cancer treatment. In industry, radioactive isotopes of various kinds are used for measuring the thickness of metal or plastic sheets. So if you want to measure the thickness of metal or plastic sheets, then we have to go for radioactive techniques. Other significant applications including use of radioactive isotopes as compact source of electric power like plutonium-238 in cardiac pacemakers and spacecraft. So this plutonium-238 is used for cardiac pacemaker and spacecraft. So as radioisotopes try to become stable, कोई भी radioisotopes होता है which whose nucleus is unstable, that's why it wants to try to stable. They transform for that purpose. They transform into new elements. Therefore, they can be converted into new elements, and that process is known as transmutation. So, radioactive decay and transmutation processes continue until a new stable non-radioactive element forms. So, for example, suppose this is the radioactive element R. It will undergo transmutation. Okay, through radioactive decay. Okay, so after that, it will be stable nucleus. Okay, so total transmutation when unstable nucleus undergoes radioactive decay and new element is formed, that process is known as transmutation. There are 118 elements, known elements, and where after 92 all elements are artificial or transmuted elements or man-made. So after 92 is uranium. Okay, so after uranium, all elements are man-made elements. They cannot or they are not found in Earth crust. Now, radioisotopes and tracers. What are radioisotopes? Radioisotopes we have discussed already, and tracers. Now we have to discuss the tracers. So isotopic tracer technique. What is this? Isotopic tracer, any radioactive element detectable in material, chemical, biological, or physical system and used to mark that material for history to observe its progress through the system or to determine its distribution. So tracer means we have to trace. If you want to trace something, we will go for tracer technique. Okay. And in tracer technique, if we are using radioisotopes, it becomes radioisotopes tracer. An isotope tracer must behave as does the material being studied. Okay, तो जो मटेरियल अपन स्टडी कर रहे हैं उसके जैसा होना चाहिए आइसोटोपिक ट्रेसर, उसको डिटेक्ट कर पाए. In addition, it must have some distinguishing property by which it can be detected in the presence of other material. So it should also have some distinguishable property. Means suppose this is the X and this is the R. So R must be distinguished from X. Then and then only we can or we will be able to detect. The movement of chemical element under study may be traced by adding radioisotopes. So suppose if you want to study any process, then we will use radioisotopes, and using radioisotopes we can study or we can trace the pathway which is being used by the chemical treatment, which by chemical element or any process. The radiation emitted by such radiation can be tracked by means of radiation detection device. So how do we use radioisotopes in tracer? For example, this is the system where it radioisotopes and our chemical element is there. Okay, now what radioactive element will do, it will emit the radiation, and these radiations are detected by devices, radioactive devices. Okay, so with this way we can trace the pathway. Radioisotopes can be detected in quantities as small as few atoms. Means if we have smaller in quantity, then we can also detect. Radioactive tracers are widely used in science, engineering, and medicine in virtual and situations. So, each and every field there are use of radioactive isotopes. Let's discuss one by one. So, use of radioactive isotopes in tracer, like first category is use of tracers in studying reactions mechanism. If you want to study the reaction mechanism, we can use radioisotopes. For example, in photosynthesis, where six carbon dioxide reacts with water molecule in presence of chlorophyll and sunlight, it gives glucose and oxygen. Okay, so how can we detect or how can we understand the mechanism? So, for example, CO2 has also oxygen, H2O has also oxygen, and in glucose has also oxygen, and in product oxygen has also oxygen. So which oxygen of the reactant is used to prepare or form or synthesize glucose? That if you want to detect, we have to go for radioactive isotope tracer. So suppose in this oxygen, in carbon dioxide, the isotopic oxygen is taken. So CO2, and where oxygen's mass is 18, and normal water means where oxygen mass is 16 is taken. After reaction in glucose, if we have the oxygen 18 mass, excess oxygen of 18 mass, then we will say that this oxygen comes from carbon dioxide. Okay, so with this way we can use or we can trace the reaction mechanism. Esterification similarly, when acetic acid reacts with methanol or ethanol or any alcohol, then it forms ester. Okay. So similarly, if we take oxygen of 18 mass with methanol and oxygen of 16 mass with acetic acid, then in the product, if we are having 18 mass oxygen of 18 mass, then we will say yes, this oxygen comes from methanol, not from acetic acid. Okay. Then we can use radioisotopes for functioning of thyroid gland. Thyroid gland, if you want to check the functioning, we have to go for this technique. Disorders associated with pregnancy. In pregnancy, there are pregnancy system is very complicated, and there are some disorders. So those can be detectable by radioisotope technique. Test of cancer growth. If we use cobalt 16, then we can find out the cancer mechanism. Sorry, not cancer mechanism, it's what cell exactly functioning in the cancer or tumor. Second category is use of tracers in industry. So there are several use of tracer technique in industry. For example, determination of the wear of a piston ring, then self-diffusion of metals, uniform mixing of metals or chemicals, H catalyst, suppose this is the reaction, ethylene addition of HBr on ethylene, then cobalt 60 is used to understand the reaction mechanism. So this way, tracer technique can be used in industry. Then effect of different phenomena on metal के ऊपर कौन-कौन से phenomena हो रही that can also be studied by radioactive isotope technique. Mechanism of effectiveness of lubricant की mechanism को भी we can understand by using the radioactive isotope tracer technique. Mechanism of reactions like spallation, polymerization, catalytic reactions, synthesis process. So there are load of industrial application of tracer technique. Now, the use of third category use of tracer in agriculture. In agriculture, tracers are also used, like uptake of phosphorus in plants, how plants tax phosphorus from soils that can be detectable, transportation of minerals in plants, minerals कैसे use होता है plants में that can be studied, irritation of maize with radioactive cobalt. With radioactive cobalt, we can understand the irritation mechanism of maize. Then fourth category is use of tracers in analytical chemistry. Maybe how can we use that, for example, to determine solubility of lead sulfate in H2O. Like this is the lead, isotopic lead, and this is normal lead. When it undergoes treatment of HNO3, the isotopic lead becomes lead nitrate, and also normal lead also converted into lead acetate. Okay. When these undergo sulfuric acid, they form different sulfates, lead sulfate. With this way, we can determine the solubility. Fifth category is use of radioisotopes in treatment of diseases. That is also known as radiotherapy. So treatment of thyroid complaint, treatment of blood disorder, treatment of cancer growth. So there are medicinal application of radioactive isotopes. Now treatment of leukemia disease के treatment के लिए भी we can use radioisotope technique where 32 phosphorus is used. Treatment of skin disease where 30 phosphorus is used. Determination of the age of Earth by rock dating method means suppose we are having or we have a rock sample, then how long it is old actually, or how old is it, so its age can be determined or can be detected or can be found or can be estimated using carbon dating method where gamma or lambda, so lambda is equal to 2.303 by t is log and not by nt. So decay with the using this formula or this technique, we can use the determination of age, determination of the age of recent objects by radiocarbon dating method. So radiocarbon dating is very popular, and with this radiocarbon dating methods, we can detect the age of fossils, trees, or whatever samples we have. So these are applications of radioactive isotopes. These are some isotopes, radioisotopes used in medicine. For example, carbon. So carbon is 14C is used, which you released beta radiation. It is used in research in metabolism. Hydrogen 3H tritium is used, which release beta radiation. Cell biology में इसका research में use करते हैं. Phosphorus 32 phosphorus is used for nucleic acid research, treatment for polycythemia. Iodine 135, iodine and 131 iodine is used for radioimmunoassay, thyroid uptake studies, thyroid scanning treatment of hyperthyroidism and thyroid cancer. Technetium 99 technetium, which releases gamma radiations used for blood flow study. Similarly, cobalt is used for 60 cobalt is used for treatment of cancer and treatment of cancer 137 cesium is also used. So these are some radioisotopes used in medicine. So thank you very much for watching this video. Please like and subscribe the channel, like and subscribe the channel. Thank you.